We learned in first lecture of this series the concept of rolling without slipping. We then learned in the second lecture the concept of torque. We will now combine these two concepts in this lecture. We start by examining this video. Four rigid body objects of different shape but of same mass are rolling without slipping down the ramp. The different colors are used to distinguish the difference in shape. Red for thin wall hollow sphere, orange for solid sphere. So please note that from the outset, both red hollow sphere and orange solid sphere look the same, but they are not actually. The mass of the solid sphere is distributed uniformly on the surface and in the interior of the sphere, whereas the mass of the hollow sphere is distributed uniformly only in the wall of the sphere. Green for thin wall hollow cylinder, and finally blue for solid cylinder. You can easily distinguish the hollow cylinder from the solid one from the outset. They will soon be released at the same time from rest. Now I want you guys to make a guess of the outcome. A. All objects will reach the bottom at the same time, or B. The object will reach the bottom at different time. Pick your choice. Well, let's play the movie to get the answer. Alright, we get our answer. It is B. The object will reach the bottom at different time. To be more exact, the orange solid sphere reaches the bottom first, followed by the blue solid cylinder. The red hollow sphere finishes in the third position, and of course, last but not least, is the green hollow cylinder. Now I'm not sure with you guys, but this result is rather unexpected to me. If I simply use Newton's second law F equal to ma, since F is the same for all four objects, in this context F comes from gravity, and m is also the same for all four objects, then acceleration A would also have to be the same for all four. That means, shouldn't all four reach the bottom of the ramp at the same time? They were accelerated in the same manner after all. From conservation of mechanical energy point of view, it doesn't make sense too. All four have the same mass. They started from the same height on the top of the ramp, which means they all started with the same gravitational potential energy. They had no initial kinetic energy because they started from rest. The track is the same for all four. Everything is the same. They should have reached the bottom in the same manner as well. This doesn't make sense to me. Is something wrong with the simulation? Perhaps it was developed unrealistically? Well, I can tell you this simulation is as realistic and physical as you could get. Indeed, if experiment is conducted using real physical objects, the result will still be the same. The problem is not with the simulation, neither is it with the Newton's second law or conservation of mechanical energy. Just like in the case of static equilibrium, our knowledge of Newton's second law and conservation of mechanical energy is not complete. In lecture 5, 6, and 7, we were talking about point particle object. Here we are dealing with rigid body object. We need to learn how Newton's second law and conservation of mechanical energy are affected in the presence of rotational motion. This is the objective of this and next lecture video. We learned from lecture 5.1 that a tendency for an object to move under the influence of force is called inertia. This inertia is reflected in the physical quantity known as mass. Objects with small mass are easily influenced by the force. Provided with the same amount of force, objects with large mass will not be easily influenced. If we apply this idea onto the motion of rigid body on the slanted ramp, we can immediately identify that this phenomenon is related to the inertia of the individual rigid body. However, this time around, it's more than just mass. Since all four objects have the same mass, mass alone cannot be the only quantity responsible for this. Our second clue comes from this simulated experiment. Here we just deal with three objects, solid sphere, solid cylinder, and hollow cylinder. They all have the same mass, and they will all be released from the same height. I will run this simulation twice. In the first run, all three of them will slide down the ramp without any friction. Let's see how they go. Well, they move together. They reach the same height on the other side of the ramp. That's because of conservation of mechanical energy, by the way. So this is what you would expect from multiple objects of the same mass being released with the same initial condition when we were still dealing with point particle mechanics in lecture 4 to 7. Of course, in this case they are not point particles, but they do behave like point particles if they are sliding down. In the second run, all three will roll without slipping down the ramp. Let's see how they go now. This time around, it repeated what we just observed in the beginning of this lecture. All three objects will still reach the same height on the other side of the ramp, and that is still because of conservation law of mechanical energy, but they move at different rate. At the moment they were being released, despite of the fact that they were being influenced by the same amount of force, remember all three have the same mass and hence same weight, the solid sphere seems to be affected earlier, with it usually move first, followed by the solid cylinder, and finally the hollow cylinder. It was as if the solid sphere has the least inertia, while the hollow cylinder has the largest inertia. Now, what's the difference between the first and second run? Well, in the second run, they were rolling down instead of sliding down. We thus can't help but to attribute this apparent difference in the inertia to the rotational motion of the object. This inertia, which is attributed to the rotational motion of the object, we have a technical term to refer to it. It is called moment of inertia. You may say it is an inertia which only becomes apparent in an object when it is rotating. Or another way of saying it, any rotating object possesses moment of inertia. What we shall learn next is how to compute moment of inertia. Let's say we have a very small object whose mass is given by delta m. The Greek alphabet delta is normally used to indicate difference in something, but in this particular situation, delta m does not refer to the difference in mass, but rather it indicates that the mass of the object is very small. How small is small? Just think of the smallest positive number you could think of. Now this object is rotating about a certain axle, as seen from the top. The distance of the object from the axle and hence the radius of the rotation is given by r1. As I mentioned just now, any rotating object carries moment of inertia on top of its own inertial mass. The moment of inertia of the object is given by the mass of the object, i.e. delta m, times the square of the radius. Moment of inertia is denoted using capital letter I. The subscript 1 is to indicate that it is moment of inertia of the object located at r1 distance away from the axle. Of course, nothing prohibits us from having multiple objects of the same mass delta m rotating about the same axle at different radius r2, r3, and r4. We can then compute the individual moment of inertia, which is given by, and the total moment of inertia of the system is simply the summation of the individual moment of inertia component. Be mindful that moment of inertia is a scalar quantity, because mass is a scalar quantity and so is radius. A radius is simply the distance between the rotating body from its rotational axis. Can we have more than 4 objects rotating about the same axis? Well, sure, why not? Can we compute their total moment of inertia? Of course we can. We just need to compute the individual's object moment of inertia and sum them up as shown here. Can we have an infinite number of objects rotating about the same axis and compute their combined moment of inertia? Well, wait a minute. What do you mean by infinite number, you might ask? That sounds like a very large number of objects. Indeed, it could be as many as you wish. Just think of the largest positive integer you can think of. It will definitely take a very long time to compute, but we have a well-defined algorithm to accomplish that. So yes, theoretically we can compute the total moment of inertia of an infinite number of objects rotating about the same axis. Now this is an important revelation. A real-life rigid body object is nothing but made of many objects of small masses such as this. Let me repeat again, this time with an animation. A rigid body object is constructed from many objects of small masses. How many is many? As many as you wish. The smaller delta m is, the more they are required to construct the whole body. As you can see from this animation, every small block which is being refilled one at a time, every one of them is a small fraction of the whole rigid body. Every one of them has a mass delta m. As the rigid body is rotating, every one of them is also rotating at a fixed radius away about the rotational axis. for every single one of them, we can compute its moment of inertia, and the moment of inertia of the rigid body is given by, which is the sum of all the moment of inertia of individual delta m. This is the formal mathematical definition of moment of inertia. The smaller delta m is, the more accurate the computation is. As a matter of fact, we have to take the limit of delta m to 0. That is to say, we have to deconstruct this rigid body into infinitely many small particles, compute the individual contribution of moment of inertia of these small particles, and sum them up to get the moment of inertia of the body. If you have learned calculus before, this is what mathematically we call integration. Again, I would like to reassure you that calculus is not required in this course, so I will not go any further than this. But do keep in mind that integration is required to compute the moment of inertia of a rigid body in general. In fact, if you know how to do integration, you will be able to derive and appreciate the different equations describing moment of inertia of the different rigid body objects. This slide shows some of those rigid body objects typically used in textbook type of question. You do not need to memorize any of them. If required in the test or exam, I will provide these equations. What is commonly shared among these objects is that they all have the same mass m. Their moment of inertia shares the same structure mr², which comes from the mathematical definition of moment of inertia itself. The coefficients in front of mr², however, are different. These differences come from the integration. If you are interested to know how each equation is derived, and hence how the different coefficients appear, we can have a discussion offline. But for now, I would like you to pay attention to the 4 objects we started with earlier: solid cylinder, hollow cylinder, solid sphere, and hollow sphere. Pay attention to their coefficients. In the order of smaller to larger moment of inertia, it is the solid sphere, 2/5, followed by solid cylinder, 1/2, followed by hollow sphere, 2/3, and finally hollow cylinder, which is 1. Remember the sequence of the object reaching the finishing line in the simulation? It was orange solid sphere, followed by blue solid cylinder, followed by red hollow sphere, and finally green hollow cylinder. Exactly in the same sequence. But now we understand why. Under the same influence of force, objects with smaller moment of inertia will rotate faster than objects with larger moment of inertia. But because they are rolling without slipping, their rotational motion is directly proportional to their center of rotation motion. Solid sphere has the smallest moment of inertia. It got accelerated earlier than the rest. It reached the finishing line earlier, and the rest follow. In conclusion, different rigid objects roll down the hill at different acceleration, despite being influenced by the same external force, because they possess different moment of inertia. Just like how inertial mass is associated to how easy or difficult for an object to be translated in the presence of translational force, moment of inertia is associated to how easy or difficult for an object to be rotated in the presence of torque or moment. Keep this in mind as we move on to the next topic on rotational dynamics.